Hi, my name is Julia Silge, and I'm a data scientist and software engineer at Posit, formerly RStudio. And today in this screencast, we are going to use a Tidy Tuesday dataset from late last year about horror movies. We're going to use the descriptions of the horror movies and show how to do some text analysis, some NLP with them. We are going to call the OpenAI API, the OpenAI famous in the news for ChatGPT and some of their other products. And we're going to obtain text embeddings for the descriptions that we have. We're going to show how to get these and then use them in R for different kinds of tasks.
All right, let's get started with these horror movie descriptions. This data set is from a little while ago. And when it originally came out, I did a kind of exploratory type analysis, made a correlation network. I'll put the link to that in the blog post when I publish this. So I'm not going to spend a ton of time doing EDA to understand this. Instead, we are going to focus on this overview, this text data where the horror movies are described. And we are going to, like I said in the intro, get some text embeddings from them. We've got other information, like an average vote, lots of different kind of horror movie information, but let's focus on the text. I noticed that some of the movies don't have an overview. And I also noticed that some of the movies are not in English. It looks like the overviews might all be, but let's filter down and get a smaller subsample of this. So we've got to have ones that have that text data. Let's only get ones that have that, I think it's original language. Let's just choose the English ones. And then let's just get a subsample because I'm going to make an API call and I want it to go pretty quickly. So let's do that. Okay, so here is this new filtered down subset of the data that I'm going to use. I set a seed so that I get the same set every night, sushi night. And whatnot here. So let's look at this. We've got title, overview, and so forth. Okay, let's just look at a few of what they are. Horror movies, overview. So let's look at like 3 at a time here. Okay, House of Usher. So this one looks to be about the filming of the movie, not so much the content. So that's something good to keep in mind. We got, we got prehistoric monsters, we got apocalypses, we've got some that are very short, some are a little bit longer, so this is kind of what the text looks like. Let's just call that enough EDA just so we can move forward in this particular screencast and get forward. So I'm going to make a API call fairly manually to OpenAI there. So I've got the documentation up here. So the first thing I need is what endpoint am I going to call? So it is a endpoint, it's like API openai.com. And the endpoint that I'm going to use is the embeddings endpoint here. So these text embeddings are I've written a fair amount about this, but like the text embeddings are representations of some text in a special space that is learned from very large data set. So I've got the endpoint I'm going to call. I need some auth. So I made an account with OpenAI and I set up an API key, and I'm going to put that here. So I need to have some headers that have my authorization in it. And then what it says in the documentation is it has to be called bearer. And then I'm going to read my OpenAI API key from my R-environ file that I've got here. I'm going to try to, I'm going to try to not print that out so that you all see my API key, and then I pay for yours as well as mine. So yeah, so this is a paid product. These embeddings here are high quality embeddings that OpenAI has created that you can use that use in models however you like. So this is not these are not open source embeddings. These are like many of these companies are starting to make these kinds of things available as like a product. Now I need to make the body of my API call. I need to choose which embeddings I want. I'm going to just use the recommended default embeddings. Again, this is from the documentation from OpenAI. So these are the text embedding ADA02 embeddings. That's the ones I'm going to use. And then I need to put in my input. So I'm going to use this exactly here. This text is what I'm going to pass in like so. Okay, so I've got the endpoint I'm calling, my authentication, and then the body. Now let's create our API call. So it's a post call. I'm going to call the endpoint. I'm going to pass in my auth. I'm going to pass in my body, and then I'm encoding this as JSON, not as like raw binary or anything like that. Okay, so moment of truth. Let's see if this works. So I'm calling to OpenAI with these thousand text, and then what I get back, hopefully, is a 200. So it worked. So now I've got. Let's look and see what it looks like. So in the response, I have got information, the headers, and so forth, and then so the next thing I need to do is I need to get out the response. So let's call it embeddings. So I call content on the response. I'll say as text, and I don't know. I think it said it was UTF-8 encoded in the documentation. So now if I look at what this is, it's just a big, huge character vector. Look, just a super long one. So what I need to next do is treat it like it's JSON. And let's flatten it. I think that will be easier. And now what I have in these embeddings is now it's a list instead of one giant just piece of text. It's now a list, and under here we have what are they, and then we've got this 1,000 length list, and each of one of these is a big huge vector. This is the embedding. This string of numbers is the embedding. So let's get that out. So I'm going to pluck. Where is it? So it's in the thing called data, and then it's in the thing called embedding. So let's pluck from data, let's pluck from embedding. And now what I have is a list with 1,000 elements, so one for every horror movie description I sent in, and then what's in each spot in the list is a numeric vector of length 1,536, and so I've got one of those for each piece of text that I sent over. So the way to think about this is what OpenAI has done is they've taken, vast quantities of text, and they have learned a new high dimensional space based on how text is used. And so picture a big space, and texts that are similar to each other are close together in the space, and texts that are different from each other are far away from each other in this space. So maybe in the big space, all our horror movies are kind of close together. But if you kind of then zoom into the horror movie descriptions, some of them are closer to each other, some of them are further away. Maybe the ones that describe what the movie is about are closer together, and the ones that describe something about how the movie is made, maybe they're further. I don't know. So what do these numbers mean, right? What is each one of these elements of the 1,536 elements? What do they mean? We don't know. I mean, that's the thing with text embeddings. Each individual element is not interpretable or useful, but altogether, these high dimensional vectors, this high dimensional space where all our text is somewhere inside of it, we can use it to understand something about the text. Okay, so we found the embeddings to kind of keep everything together. Let's put it as a embeddings like this. So let's call this. So this is so I don't make a mistake in terms of which embedding belongs to which movie. So if we look at this, so we've still got all that original data we have, but now we have a new column. So if we say select, let's see, like ID, original title, embeddings, if I just want to look at what's here, we have, so for every movie, we know what title is, and then we have one of these embeddings, one of these vectors. So maybe sushi night, is at one. What these numbers represent is where in this high dimensional space is the description of sushi night. Where is the in the high dimensional space is Ozark sharks or Sharktopus. Okay, this is pretty great. I am gonna love this, I think. Okay, so this is kind of in a tidy format. Some of what I'm gonna do is not very tidy data-ish. It's gonna be more matrix based. So let's make a matrix of this. So what I want is a matrix where every row is a movie and every column is one of the elements of the OpenAI text embeddings. So I think the best way to do this is just to unlist everything, or embedding. So this is that column. So I'm just going to unlist the whole thing, and then I'm going to say how many columns is it supposed to have? This many. And then I think I have to say by row equals true. And let's call this the embeddings matrix, like so. Yes, okay. Did that work? Yes. So what is this matrix? It's just a matrix of numbers, right? And we don't really know what the numbers mean, but we have a row for every movie, and we have a column for every for every element of the OpenAI text embedding. So it's specific to this model, this text embedding ADA 002 model from OpenAI. Like that, these numbers are specific to that. So we can compare them with each other, but we don't really know what those numbers represent. They're not super interpretable on their own. Okay, so we've got it. We did it. We went to OpenAI. We got the embeddings that we're interested in, and we matched them up to the movies they belong to, and also made a matrix, because that will be more useful for some of the things that we're going to do here. So you can do a lot with these numbers. You can use them as features for a supervised or predictive model. There's some interesting work lately about clustering these, and you can use that as topic modeling. I'm just going to show two kind of basic applications of what you might want to do with these kinds of embeddings. So the first thing is similarity. How can we find which movie descriptions are similar to each other? So I'm going to compute a cosine similarity matrix. This is pretty sim. Sure, let's do that. Embedding similarity. So I'm going to take the original matrix. I'm going to scale it by row sums of this multiplied together. So I'm going to multiply it element wise, sum it up, square root. So first I'm going to scale by the length, and then I am going to find the cosine similarity here. So I'm going to do matrix multiplication. Is that right? I think that's right. With the transpose, like so. And then let's just double check that turned out the way I thought it would. Yes. Okay. So now we have 1,000 by 1,000 matrix. So what this is doing is it's comparing every horror movie with every other horror movie. And so if I don't know if I want to print it out because it's kind of big and it gets so slow after you print out really big things. But if we looked at it, it would have ones on the diagonal, because it would be a symmetric matrix. Ones on the diagonal where things are compared to themselves, and then all the other elements will show how similar that movie is to other movies. So let's look. How do we see which movies are similar to each other? I don't know. I'm pretty compelled by Sharktopus, so let's start with that. Okay, horror movies. So that one is the fourth one. There, Sharktopus, and let's just look at the like title and the overview. Oh man, this looks this looks so good. Okay. Are you gonna pop up for me? Okay, so half shark, half octopus, built for combat, but then it escapes and terrorizes the beaches of Puerto Vallarta. Okay, all right, so that is a text. Let's say I'm interested in that text, and I want to find texts that are most similar to that. So what I can do is I can pull out from the similarity matrix. I'm going to take the fourth row here. So it is so that will be the one um for Sharktopus here. And so this is for all the 1,000 movies that we have. How similar is it? So the fourth element is 1, because that's where Sharktopus is compared to itself. And then this is going to be symmetric around the diagonal. And so notice we've got a lot of 0.7, some 0.8. So if let's find, I want to go back to something a little tidier here because I think that will be easier for me. Okay, so here they are. I can make this a little more clear. What are these things? This is the movie. This is the value equals the similarity, like this. So for every movie, this is a similarity to Sharktopus. Compared to itself, it is perfectly similar there with a 1. So now we can arrange by descending similarity like this. And so now we have the most similar movies to Sharktopus. So let's see what these are. So let's go to horror movies. Let's take the first couple. So I can take 935, 379, 380, like that. And let's select the title and the overview so we can kind of see what it is. Okay. Oh man, see, this worked so well. Look, like this is what similarity does. So Sharktopus is a half shark, half octopus, but the third most similar thing is a mega shark versus a giant octopus. Dark waters, moneyless ocean exploring. Oh goodness. Okay. But again, it's the ocean, the coast is being terrorized, and Octoman. So we've got like an octopus type thing here. So this worked really well, right? And so what we're seeing here, so remember, super high dimensional space, the horror movie descriptions are all somewhere in that space, and then what we've done here, we find how similar are they all to each other. I'm going to pick one that I just want to explore a little more deeply, and then I found the closest in the space to Sharktopus is things like Octoman, Dark Waters, and so forth. All right, so that's similarity. Let's talk about principal component analysis. So I love principal component analysis. It's one of my favorite things. It's like, I don't know, it seems magical or whatever. I'm going to set a seed because this is, you can go positive versus negative, depending on where the algorithm starts. Okay, I usually use this implementation of PCA because it's really fast. And let's put in our matrix. So we're back to our original matrix here. And it's going to do some nice math for us. We could do we have 1,000. So let's find the first 32 principal components. I'm going to call this horror PCA like this. Okay, so let's run this. Look how fast. So nice. It's especially good if you have sparse data, which this is not. That's actually part of the reason why people use embeddings for text data is we have, you saw we had 1536 columns here, but compared to how sparse text data is, you can easily 10 times that, 100 times that, right, to get, or maybe not 110, you can easily 10 times that if you're looking at just words. And so these embeddings are like a more dense representation of language data. It's both more dense and has learned the structure of language to make these. Okay, so we have our PCA here, and now we can explore that. So, I'm sure a lot of you know this, but principal component does is it takes the high dimensional space we had, which was the embedding ones, and it learns a new, special, different high dimensional space. So it's like a transformation of the space, and in the new space, the components are created or chosen or learned such that the first principal component, so like the first axis of this new space, explains the most variation in the horror movie descriptions. The second is the second most variation and that type of thing. So this horror object, if we were to look at it, I think that is a good way. Nice. Very nice. So it's got a couple of things in it. It's got the standard deviation, like whether it was scaled or not. This what is called rotation. That is the matrix of the eigenvectors. And then this one is the original data that we had multiplied by this matrix, i.e. it's been projected into the new space. So, we could do something with the eigenvectors themselves, but let's do something with this matrix here. I am going to make it into a tibble here to try to get back into some tidy data land, like so. So we've got the 32 principal components, and it's a bunch of numbers again. And again, we're like, what do these numbers mean? Well, at least I have a little better understanding of what these mean. So in principal component 1, we've got 1,000 rows. So each row is a movie again. And principal component 1 is in the new principal component space, which is where principal component 1 is the one that explains the most variation. How different is the text as these texts are described? How the horror movie are described. Where is it along principal component 1? Where is the movie? And so forth about principal component 2 and moving up. Okay, again, let's bind this together with horror movies, the original data. And let's call this is like an augmented PCA. I didn't use Broom here. I did it kind of manually. But now we have the principal components together with things like the title, the rating, all the stuff that we know about them. So we can make a plot. So let's take let's do those first two principal components, PC1, PC2. Let's put them on a point in points here, like that. So we're gonna have 1,000 points on our plot. Okay. There's no like clusters here. We can see that. Let's say alpha, so we can see where they are. We can look for other information here, like maybe we can map this to the color to the vote, maybe. I think it'll be a little easier to see if we use like a Viridis color scale. Viridis C for continuous. Okay, so so one thing I notice here is where the vote is not related at all to the text. So we're not like movies that are described in one way are, it does not look like there's any relationship here. So that is interesting, right? Like that you can't really tell if a movie is going to be highly rated or not based on how it is described. I'd like to kind of know which of these are which movie. So let us let's use Plotly, which is kind of my go-to for a quick interactive plot. So we do this, and then we do GG Plotly P, like that. And so now it's interactive here. And so I have the information. I want to see the title though. So let's say I have to put that, if I remember right, I do something like text equals title like that. And then I can say tooltip equals text like that. All right, and let me make this a little bigger so we can look at it. And so now I'm seeing what the titles are. Happy Tree Friends Winter Break. Doesn't sound very horror-ish, I gotta say. Okay, nice. Okay, so for example, oh, look, it's our friend Sharktopus. Sharktopus is actually is an outlier, like way down in this end. And what else is here? Ebola Rex versus Murder Hornets, Green Slime. Oh, there's Mega Shark versus Giant Octopus, Aquapolyx. So from beyond, maybe this is like the ocean monster kind of section over here. And then we can look, I don't know, let's go look straight over here. Okay, so we've got things like dolls. These sound all very like sexy. Sexy horror. We've got things that are like very very sexualized kind of horror here, which apparently is very different. Yeah. This is like the sexualized horror section over here. So apparently that's like very different from what we have over here with the ocean monsters. And I can't really tell. We don't have the information to say, PC1 stretches from monsters to people. Like we can't really say that, but we can interpret it by looking at what they are and using our information that we know about these. I don't know if I'll be able to say, oh, this is all like night. No, maybe it's like, and what's over here? Okay. I'm not sure. I'm less sure what's going on in this direction. I would probably have to learn a little bit more about the horror movies that are in this. So, to sum up, we got the text embeddings. We matched them up to the movies that we had, and then we were able to find similar movies in the original embedding space. And then we found a new space, the principal component space, where we are explaining variation.
All right, we did it. We got the text embeddings. We connected them to the horror movie, other data that we had. We showed how to find similar horror movie descriptions, and we showed how to use PCA to understand how different the text is, to understand which texts are most similar, and like what explains the variation that we have in the text that we have. Whenever we talk about text embeddings, it's really important to understand some of the caveats and the limitations that exist around using them. I've written about this before in the blog post. I'll put some links to different places I've written and spoken about text embeddings and the limits of them. The big issue is that they're trained on enormous data sets of language, and the biases that exist in human society are like literally encoded in those numbers. So when you were looking at that, 1536 length, those 1536 length vectors, keep in mind that those are vectors that have basically been imprinted with human bias, because they're trained on large data sets of human language. OpenAI themselves talks about this, and if you look at their documentation, I'm quoting here, it says, the models encode social biases via stereotypes or negative sentiment toward certain groups. So even in an example that's kind of silly, like the one, or fun, or whatever, like the one with the horror movies, this is still something that's really important to be aware of whenever we use them, and to understand how we can know how this will affect any application or analysis that we're doing, and any options that we may have to mitigate those kinds of effects. So I hope this was useful, and I'll see you next time.